Hi, I'm Sean Law, the creator and core developer of STUMPY. You can follow me on Twitter at SeanMyLaw, and you can also follow the development of STUMPY at Stumpy_dev. I'm super excited to be here today to tell you about modern time series analysis with STUMPY and help you take your time series analysis skills to the next level. First and foremost, I'd like to say thank you to all the PyData global organizers as well as volunteers for putting on such a great conference. And I'd also like to acknowledge my employer, TD Ameritrade, for giving me the opportunity to speak here today. At TD Ameritrade, I work in a research and development group called the Exploration Lab. There, I'm a senior applied research scientist and lead data scientist. So what's the problem? We're talking about time series data analysis here. And we've all been there where maybe you have a collaborator, maybe your boss or a manager. Let's say, here's some time series data. Now perform some magic, Dr. McFancy Pants. And if you're lucky enough and the data set is small, maybe with 10 data points, you might be able to visualize it and observe an increasing trend. Maybe it's 100 data points and it's still manageable. And you can see it goes up, maybe it looks bimodal, you can compute some statistics from it. Now, once we get to about 1,000 data points, we might see that there is a periodic trend or things happening or some seasonality. And once we go beyond this to about 10,000 data points or more, it becomes a lot more challenging to visualize. If I were to ask you, can you spot anything interesting from this time series data? Any patterns, any anomalies, any outliers? The point here is that it's very, very hard to see. Now, I want you to keep this picture in mind because once we get to the live demo, we'll revisit this and we'll use STUMPY to analyze this data. And I don't know about you, but when I look at the left-hand side of this plot and then I shift my eyes to look at the right-hand side, I've already forgotten what I've looked at in the first place. And usually after that, I just feel this overwhelming sense of dread. And I just hope that there's some magic spell that I can cast to sort of wish it all away, or at least tell me where I should focus my attention on. And that's why we're here today. Now, here are some of those common magic spells. We talked about visualizing the data, but once it gets large, it becomes untenable. Now, you can also reach for our good friend statistics. We might plot mean, median, modes, look at other global statistics like the max and min, but very rarely when we're looking at time series data are we interested in single point statistics. We're really interested in context, maybe sequences along the way. You can also build an autoregressive model, but this also makes it a key assumption that there is something repetitive about your data. And you can also reach for anomaly detection. But what does an anomaly look like in a time series? Right? And also, if you see it once and then a second time, is it still an anomaly? So defining what you mean by anomaly really matters, and it's really hard. You can also perform forecasting on your time series data, maybe using Facebook profit or some sort of additive, building some sort of additive model. You can also build machine learning model, whether it's a linear logistic regression or a gradient boosted trees. But now you might have to think about how do you interpret the results or the model itself. You can also reach for unsupervised learning methods such as clustering, where you're clustering your time series. But even that's pretty hard. And of course, there's dynamic time warping. So if you have data sets that are of different lengths, how might you compress and stretch them out in order to compare them? And of course, in the age of artificial intelligence, we can't forget about deep learning, everybody's sort of favorite hammer looking for a nail to hit. And now you need a ton of data and also a lot of compute power in order to process this. And the point here isn't that to point out all the pros and cons of all these different methods. The point here is to remember that there's no silver bullet and there's no free lunch. Every method that you reach for comes with some sort of compromise. Each method is good at different things. And hopefully what you'll take home today is that even a method like STUMPY can be used in addition to all these other methods, right? So it's another tool to add to your tool belt. But hopefully you can iterate quickly and hopefully get to your insights quicker too. So let's start with an illustrative example. Here's a time series of length 13. Anything interesting about this? You might notice that it's bounded between 0 and 15. Are there any repeating patterns? What if we plotted it? You can see that there's some highs and some lows. Let's start off with a definition. A subsequence. And you're going to hear me say this word many, many times. So a subsequence is simply a part or section of the full time series. So for instance, this could be a subsequence. This could be a subsequence of length 3. This could be a subsequence of length 8. So what's the goal? We're thinking about time series analysis. And if you think back to some of the magic spells that we just covered, many of those approaches make a key assumption that there is some sort of conserved behavior, or perhaps a pattern that repeats itself. And so our goal really should be to think about, if a behavior is conserved in your time series, there must have been a reason why it was conserved. And teasing out these reasons and these causes is often very, very useful. Okay? And so that should be our goal. And we can digest this and summarize this by asking two questions of all of our time series data. Number one, do any conserved behaviors exist in my time series data, or do any patterns exist? And if there are conserved behaviors, what are they and where are they? To answer these questions, I like to use Occam's razor, which states that simpler solutions are more likely to be correct than complex ones. So we're favoring simplicity over complexity. And so we should ask ourselves, what's the most simple and intuitive approach that we can take to analyze our time series data? And some of the qualities that our approach should have is that it needs to be easy to interpret. So if you come back 3 months later, you don't have to perform any mental gymnastics to interpret your data. And also needs to be user and data agnostic. So anybody can use it and hopefully be able to apply it to any time series. Also, our approach should require no prior knowledge. So thinking about machine learning, where oftentimes you have to train the model first before you can perform a prediction. In our particular case, we want an approach where we don't have to train and predict. We just analyze upfront. And then last but not least, we want our approach to be parameter-free, or essentially be parameter-free. And if we were forced to choose a parameter, that parameter would be intuitive and obvious, and that parameter is not so sensitive to the method that we choose. So for instance, in time series analysis, one of these parameters might be the subsequence length. So we call it M. And so in this particular case, there's a subsequence of length 4. Now that we've established this, we can ask ourselves, how might we compare subsequences? So how might we compare this green subsequence to this blue one on the right? Now, one of the most obvious ways to do this is to compute something called the Euclidean distance. And it's simply the straight line distance between 2 points. So what does this mean in practice? So if we take these two subsequences, no, you know what? Let's shorten them. Just to start off with a simple example. We have our subsequence on the left called x. It's got 2 points, x and y. And our subsequence on the right called y with also 2 points, y1 and y2. We can plot them, x over here, y over here, and we know that the Euclidean distance is just a straight line distance between them. Let's just call it h for simplicity. And intuitively, we know how to compute h. Once we draw a right angle triangle, label the sides, we actually know that h squared is equal to a squared plus b squared. And hopefully you'll recognize this as nothing but our good friend Pythagorean theorem. And once we plug in our numbers, we actually find that h is actually equal to square root of 2. So the distance between these two subsequences, root 2. Extending this to our original example, where our subsequent sequences were of length 4, we see that we have an x3 term and a y3 term. And now we update our Pythagorean theorem with a c squared term. And we also have an x4 and y4 term that we now have a d squared term that's covering that. So as you increase the length of your subsequences, you might have an e squared term and an f squared term and so on and so forth. So this is extensible. And we can plug in our numbers and find that the distance between these two subsequences is square root of 67. And that's it. But this is the case where somebody gives you both of the subsequences and you can compare them. But what if we wanted to take the green subsequence and say, is this subsequence conserved across our time series? Then what we can do is compute pairwise Euclidean distances. To do that, we'll repeat our time series and we'll create a blue subsequence that we'll compare against. And then we'll record the distance between the green subsequence and the blue subsequence in this vector down below. So in this particular case, the green and blue subsequences are identical, so the distance is 0. And I'll slide that blue subsequence over, compute the distance, and I'll continue doing this all the way until I run out of subsequences to compare with the green one. And what we end up with is something called a distance profile. Pretty straightforward. Now, if we were to ask, is that green subsequence conserved anywhere in this time series? What we do is we look at our distance profile and look for the smallest value. In this particular case, the smallest value is 0, and it's showing that the closest one is the self-match, or often called the trivial match. Now, this is pretty obvious. We're not that interested in this one, so we often just ignore this one, and we slide across again, looking for the next closest match, and that happens to be this blue subsequence here. And the green and the blue subsequence have a distance of 6.9 away. Nothing else is closer. Now, we don't only have to do this with the green subsequence that we're showing here, but we can actually just keep sliding that green subsequence across and computing all of the possible pairwise Euclidean distances and all of these distance profiles. And then once we stack them on top of each other, remove the unnecessary parts, what we end up with is a distance matrix. And this is an exact distance matrix. There are no false positives. We've computed all the distances, and it's pretty intuitive. And so what's the most simple intuitive approach? I'd say that this distance matrix approach is pretty straightforward. It's easy to interpret, and it checks all of the boxes in terms of all the key qualities that we're looking for. But wait, there's got to be a catch. It feels too simple. We should really be asking ourselves, is the solution scalable? And so if we were to ask, how might we perform a brute force calculation to compute this distance matrix? So let's start with some Python code. So we define our time series up above with a length of 13 and a subsequent length of 4. And our time series is also down at the bottom for illustration purposes. And to compute the distance matrix, it actually just requires 6 lines of Python code. I don't know, focus your attention on these 3 for loops. The first for I loop corresponds to sliding this green subsequence across. This for j loop focuses on sliding the blue subsequence across as well. And the for k loop is for computing your Euclidean distance. And if you're thinking about, well, what is the computational complexity? It actually takes O of n squared by m time to compute this distance matrix. And also, to store this in memory, it would take O of n squared time. To put this into perspective, here's a back of the envelope calculation. Imagine you have an IoT sensor that was collecting data for 5 years, 365 days a year, 24 hours a day, 60 minutes every hour, 20 times every minute. That means that for 5 years straight, every 3 seconds, your sensor would be collecting a data point. This would result in just over 50 million data points in your time series data. And if you were to use your brute force method to compute the distance matrix, it would take roughly 4.4 years to compute and over 11 petabytes of memory to store. And so if we ask ourselves, is the solution scalable? Sadly, it is not. And it kind of explains why all of these methods are so popular and people are still using it to this day. It's because this distance matrix, while it's intuitive and simple, it just wasn't scalable. That is, until today. So back in the December of 2016, the researchers at the University of California, Riverside, under Eamon Keogh's group, as well as at the University of New Mexico, under Abdullah Mouin's group, published a series of back-to-back papers describing something called a matrix profile. And really what a matrix profile is a vector that stores the distance between each subsequence within a time series and its nearest neighbor. Believe it or not, you actually know what this means. Going back to our illustrative example, starting with the distance matrix, a matrix profile is simply taking the nearest neighbors to each subsequence, which is exactly where those green boxes are, and pulling them out and only storing these. So this is your matrix profile. Now, you still have to compute all of the distances just so that you're avoiding any false positives or false negatives. But really, the good thing here is that this is now stored in O of n space. And these academic researchers later went on to claim that you can actually compute this full distance matrix in O of n squared time. And using this matrix profile, you're actually able to answer the 2 key questions that we posed at the beginning. So how might we use our matrix profile? So the first thing that we do is, going back to our illustrative example, is we might annotate our time series using the matrix profile. And we might even plot it just to look at it. And you might observe that there are some high points and some low points in our matrix profile, right? But to interpret this, let's say for this particular green subsequence over here, what this is telling you is that its nearest neighbor is located at 6.9 units away. We don't know where it is along the time series, but its nearest neighbor is 6.9 units away. This particular subsequence has a nearest neighbor that's a little bit closer at 1.4 units away. And all the way at the very end, this subsequence, its nearest neighbor is at a distance of 6.2 away. And what we might now do is ask the question, are there any conserved behaviors in our time series? To do that, we just simply have to look at our matrix profile and identify the minima, whether it's a global minima or the local minima. In this particular case, we find that the global minima are shown here. And the one on the left corresponds to this subsequence, and the one on the right corresponds to the blue subsequence. And these, you can understand why these are a particularly conserved sequence, because the first data points are both 1s, The next one, 3 and 2 are very close. The third one, they're both 2. And the last one, 9 and 10, are also very, very close. And this global minima is often referred to as a motif, or a potential pattern, conserved pattern. And using the same approach, you can identify other conserved patterns as well. Now, there's another definition, which is the matrix profile index. And that's the index location of the nearest neighbor for a given subsequence. So for the subsequence shown in green, its nearest neighbor is actually shown on the right. But one thing I want to point out is this index up at the very top is a zero-based index, just for reference. So the subsequence on the left, its nearest neighbor is located at index 8. The subsequence on the right, its nearest neighbor is located at index 1. And in fact, all the subsequences have a nearest neighbor shown at the indices down below. So to drive home this point, this particular subsequence has a nearest neighbor that is a distance of 6.2 away and is located at index 2 with the same length. And that it's this subsequence over here. Another thing we can do with the matrix profile is identify potential anomalies. To do this, you look for maximum along your matrix profile. And that happens to be this value here. This is the biggest number along our matrix profile. And that corresponds to this subsequence here. And this is a potential anomaly, or in time series parlance, this is known as a discord. And there are many, many other things that you can do with matrix profiles, but we'll cover them in our documentation. Now, we discussed how the brute force method takes O n squared by m time. These academic researchers published their first paper detailing an algorithm called STUMPY, which uses fast Fourier transforms and convolutions to reduce that computational time down. They then published a follow-up paper called using an algorithm called STUMPY, which further takes that time down to O n squared. And then they ported that algorithm over to GPU hardware and just showed that for a time series of length 100 million, which is double the number of data points that we showed for that brute force calculation, using the GPU STUMPY algorithm, they were able to compute a exact matrix profile in just over 12 days. And this is Eamon Keogh, one of the original researchers, and he states that given the matrix profile, most time series data binding problems are trivial or easy to solve in just a few lines of code. And they later went on to say that these are the best ideas in time series data mining in the last 2 decades. And anybody who says this, in my opinion, must be a real gangster. But of course, extraordinary claims require extraordinary evidence. And this was stated by the late Carl Sagan. And this brings us to STUMPY. And really, STUMPY was developed to validate a lot of these claims, to see if you can really compute these matrix profiles efficiently and quickly. And so STUMPY is a powerful and scalable Python library that efficiently computes a matrix profile so that you don't have to reinvent the wheel. And then once you have this matrix profile, you can use it for a variety of time series data mining tasks. STUMPY has been around for just over a year with over 50,000 downloads and installs and over 1,500 GitHub stars. So a lot of growth and a lot of support from the community. We're at version 1.5, and you can conda and pip install it using the ConForge channel. And we have minimal dependencies. Assuming that you're using a modern Python, we use NumPy, SciPy, Numba, and parallelized across all of the cores on a given server. And if you just so happen to have a Dask cluster available to you, you can actually pass in that Dask client or scheduler to STUMPY, and it will distribute that computation across multiple servers. To give you an idea, remember that 100 million data point sample, computing the matrix profile in just 12 days, we actually were able to compute the same matrix profile using 256 CPUs across 32 servers in just under 10 days. So I'm not saying that CPUs are faster than GPUs, but certainly that STUMPY can scale very, very well. We call our version of the algorithm STUMP. It's a play on words. The U pays homage to Numba and NumPy. And the distributed version, ending in ED, is called STUMPed. We also have a GPU version called GPU STUMP that is highly performant, that scales to larger data sets. And if you ask us, is the solution scalable? We'd say a resounding yes. And to use STUMPY, it's pretty straightforward. You have your time series, TS, and your subsequence length, M. You call STUMPY by saying stumpy.stump, pass it your time series and your subsequence length, and you're done. And if you have a larger data set, you can actually use the GPU version, which has the same essential API, and the only difference is just 4 letters. In addition to STUMP and GPU STUMP, we also support multi-dimensional matrix profiles using MSTUMP or MSTUMP for the distributed version. You can also compute an approximate matrix profile, maybe using 1% of the computational time using our SCRUMP implementation. And last but not least, if you have streaming data and you want to update your matrix profile as new data points are coming in, you can also leverage our STUMPY or incremental STUMP version. So why should you use STUMPY? A couple of really important reasons. First, STUMPY is super user-friendly. It's developed for data scientists by data scientists. And also, STUMPY is very interpretable. If you understand Pythagorean theorem, Euclidean distance, you've got this. But more importantly, STUMPY is fast and scalable. So we have multi-CPU and multi-GPU support out of the box without any additional dependencies. And STUMPY is highly reliable with 100% code coverage always. And it also is highly complementary. And it brings us to the point of when should you use STUMPY? STUMPY can be used in combination with any of these methods as we mentioned before. And it's highly complementary. But the point here is to remind you that there is no silver bullet and there's no free lunch. You should really use all of these methods or as many of these methods as possible. But the great thing about STUMPY is that it is now a scalable and performance solution that you can reach for immediately. So we're going to change gears now and move towards a live demo. So in this demo, I want to draw your attention to this raw time series up at the very top. You might recognize this time series as being the same time series that we showed and discussed at the beginning of our talk. Now, as you're focusing your attention on this time series, do you spot anything interesting? Are there any insights that jump right out at you? Perhaps you can spot maybe that there's a pattern that repeats itself. Maybe not. Or are there any anomalies or outliers that speak to you? What if I showed you what you were looking for? Now, this particular pattern or the subsequence shown in green here actually repeats itself one time somewhere along the time series. And I've blown it up here and zoomed in on it just so you can see all of the finer detail. Now, as you go hunting across this time series, can you spot where its nearest neighbor is located? So, not to belabor the point, but its nearest neighbor is actually located all the way to the far right, shown in the gray subsequence there. And I've actually plotted the gray line down below here. So you can see that they're a pretty close match, but not exactly the same. And in fact, their distance is 5.5 units away from each other. So it's not 0 because they're not identical, and it's a 5.5 because there's some differences over here, some differences over here, but for all intents and purposes, you'd agree that the green subsequence matches the gray one. And to the astute observer, you might have noticed that below our time series, I've also plotted the matrix profile. And so what you might have observed is that in our matrix profile, the global minima is located over here and also all over here. And this actually corresponds to a motif. So the green subsequence and the gray subsequence correspond to a motif or conserved pattern or conserved behavior. But what's really nice about our matrix profile is not only do we get these global motifs, but we actually get the nearest neighbor for every single subsequence along our time series. So when I press play, the green reference subsequence will slide from left to right, and you'll observe that the gray subsequence will change and update in response to the changing green subsequence. That's pretty cool, right? Another thing that I want to point your attention to is for every green subsequence, its nearest neighbor can occur not only to the left, but it can also occur to the right. So this means that your nearest neighbor can happen in the future or in the past. And in time series parlance, when it occurs on the left, that's called the left matrix profile. And when it happens on the right, that's simply referred to as the right matrix profile. And generally, we're most interested in the global matrix profile value. Now, another interesting thing that we can do here is not to only look at the minima along our matrix profile, but we can also look for anomalies by investigating the peaks. So in this particular case, this green subsequence, again blown up at the bottom here, has the largest matrix profile value. That means that its nearest neighbor has a distance of 23.5 away. No other subsequence along this time series has a nearest neighbor that is that far away. And its nearest neighbor is now overlaid with it here. And you can see that there's a lot of differences, a lot of deviation from this green subsequence, right? And so this is a discord or a potential anomaly. But I want to remind everybody that in the case of a pattern or anomaly, I'm telling you what you should be expecting and looking for. But if you think back to our original process of analyzing a time series, usually what you get is just this raw time series up above. And hopefully you can understand now that you can leverage the matrix profile to tell you where you should start looking first. So you would start with this time series, you would feed into STUMPY and compute your matrix profile. And then by simply exploring the minima, it tells you where your conserved subsequences are. And by exploring the maxima, you will identify where the anomalies are as well. But also you get all the information in between. And this is really just scratching the surface. In addition to computing the matrix profile for a single time series, you can actually use STUMPY to compare two different time series A and time series B. And that's often referred to as an A-B join in the literature. So what this means is, when you take time series A, you're asking if, for every single subsequence within time series A, what is its nearest neighbor in time series B? Or to put it differently, you're asking, are there conserved behaviors in time series A that can be found in time series B? And that can be done using STUMPY. Another useful resource is our documentation. In our README, you can find short code snippets that will help you get up and running really quickly. The installation guide outlines how you will conda or pip install STUMPY. Additionally, the STUMPY API outlines several useful functions that you might use to either compute matrix profiles or to take that matrix profile and extract other insights from it as well. Last but not least are our tutorials. These tutorials provide very detailed code snippets as well as plots and figures that reproduce examples from published work. So we encourage you to dive into these tutorials and learn more about the many different things that you can do with STUMPY. So coming back, I know we've discussed a lot of different things. First and foremost, we've talked about motif and discord discovery, so looking for patterns and anomalies. We've also talked about how you can use MSTUMP for multidimensional matrix profiles. So if you have multiple sensors collecting, let's say, humidity, temperature, and pressure all at the same time, you can analyze which of those time series are important. You can also do something called time series chains, which is related to forecasting. And also semantic segmentation, sometimes known as, let's say, change point detection, where you can detect whether there's a regime change within your time series. Matrix profiles and their indices are great as inputs to machine learning features. You can also compare and cluster time series using something called MP-DIST. And many, many other things can be done using matrix profiles and using the STUMPY package. Final calls to action. We'd love to look for new contributors, especially if you're a minority in technology. We'd love to work with you. Also, we'd ask you to communicate. Tell all of your friends and colleagues about STUMPY. And finally, consume and use STUMPY. It'd make me really happy. Just putting up some links here. If you're looking for STUMPY and your favorite search engine, search for Python STUMPY. All of our very verbose and informative tutorials can be found in the link shown there. The live demo that we showed earlier can be found in the demo link. Also, we have a wonderful Google, how you can leverage the Google Colab GPUs. All the code is open source and on GitHub. And as well, we have wonderful documentation that you should check out. And last but not least, thank you for taking the time to learn more about STUMPY. And stay safe out there. Bye-bye.